Okay, let's begin. So the format is as usual. We'll have two talks, 20 minutes each, followed by 10 minutes of questions. If you do have a question during the talk, then please type it in the chat, preceded by question, and then we'll get to it after the talk. And you can also speak out after the talk if you have more questions. In between, we will have a 10-minute coffee break where you will all move uh, to, to a separate room and you can talk to each other over a cup of coffee. Our first speaker is Emin Berker from CMU. Emin, could you please start sharing your slides?
Fine, thank you. Can everyone see my screen?
Yes, all good.
Perfect.
Okay,
Uh,
the screen is yours.
okay. Thank you so much, Florian, for the introduction, and thanks everyone for coming. It's so nice to see so many familiar faces. So I'm going to present to you our paper called "How Many Votes is a Lie Worth?" This was a very fun project to work on, in large part thanks to my great co-authors. Eden is here, I think, who deserves the credit for much of the slides. So I'll go ahead and get started. So subtitle of this paper is Measuring Strategy Proofness Through Resource Augmentation. And to explain what that means, let's dive in with a story. So it's election day in Wonderland, and Alice is going to cast her vote. She really wants her top candidate to win. But a little known fact about Alice is that she is a well-versed student in computational social choice, thanks to a class that she took during her undergrad years. And her favorite lecture from this course was on strategic manipulation. And from that lecture, she actually remembers that every single reasonable voting rule can be strategically manipulated. And this is when she realized that she can also benefit from misrepresenting her preferences in this Wonderland election to get her favorite candidate to win. But as she thinks more and more about this lecture, she also remembers that, in fact, manipulating, like finding the optimal manipulation, is computationally difficult for many common voting rules. And not only that, but it also requires information on the preferences of others. And in fact, if she misestimates the preferences of even a small fraction of the votes, then she can actually hurt herself by manipulating rather than help herself. This is a great paper by Eden over here. And she's thinking about it and she's getting more and more stressed. Even if she knows the preferences of the other voters, there might be other forms of uncertainty, such as people's preferences changing rapidly or people not knowing who will actually show up to vote in the election. And worst of all, she's really scared that other people might be strategizing themselves. And as a result, the information that she has on these voters might be cleverly handpicked in order to exploit Alice. And so she's now really scared about this idea of manipulating. And in midst of her despair, she actually remembers that she has a secret weapon, which is a car. In fact, in particular, she has all these neighbors in Wonderland, and Alice's neighbors, they have the exact same preferences as her. The community show they have the top candidate. They share like their opinions with each other, and moreover, these people are not gonna vote because they're so busy with the Tea Party, they cannot bother to show up in the polls unless someone drives them. And Alice is really happy to be this person to drive her neighbors to the polls because, in particular, unlike finding the optimal manipulation, which has all these difficulties that we just talked about, driving her neighbors who share her opinions requires no computation, no information on the rest of the elected, or even on the voting rule being used. So now Alice has a choice. She can either spend all her time during election day to get information on other voters and compute her optimal vote, or she can hit the ground running, just driving these neighbors that share her preferences to the polls and try to get her favorite candidate to win by getting out the vote, so getting more support to her favorite vote. So, to her favorite candidate. So, the question that we're interested in this paper is that just how many of these truthful neighbors that share Alice's preferences should Alice drive to the polls in order to be sure that what she achieves with that strategy is as good as strategic voting? Another way of saying this is how many truthful copies does a voter need in order to ensure that they produce a result as desirable as her best manipulation. So so for any reasonable voting rule, for most rules at least, you would expect that if you add enough copies of yourself, then you're going to get what you want, because most of these rules favor overwhelming majorities, and that's why getting more people like you will naturally skew the election in your direction. However, this number might look really different for different rules. And here's one example to demonstrate that. So this is a preference profile. With this crowd, I don't think it needs much introduction, but we have m number of candidates, in this case 4, n number of voters, in this case is some large number larger than 9. And we call this the preference profile, the vector of the preferences of all voters. Each voter's preference is a strict and complete ranking over all the candidates. So in this case, voter 1 likes candidate 1 over candidate 2 over candidate 3 over candidate 4. Voter 2's favorite candidate C4. And these 3 groups of voters are grouped up together because they share the same preferences. Okay, really good. So now let's introduce 2 voting rules. Again, with this crowd, I'm sure there will be people familiar with them. But with instance runoff voting, the candidate with the least number of voters that rank them top out of the remaining candidates get eliminated. So in this case, C1 would go first because there's only 1 voter that likes them best, whereas everyone else has at least a couple. And then with C1 gone, now C2 is going to have a little edge over C3 because voter 1's vote is transferred to C2. So now C3 is the candidate with the least number of top choices. So C3 is going to go. Then it's going to be an election between C2 and C4. You can see that these 2 groups are going to cancel each other out. These 2 voters are going to cancel each other out. And C4 is going to win. So the instant runoff winner of this election profile is C4. Another voting rule that's quite common is Borda count, where every voter gives m minus j points to their jth ranked candidate. Remember that m is the number of candidates here. So if this was this case, they would give 3 points to their top choice, 2 points to their second top choice, 1 point to their third top choice, and 0 points to their bottom choice. So if you believe me, not that I've given any reason to believe me, but these are the border points of the candidates in this election. And in fact, you can see that C4 once again has the most number of points because we've assumed that n is at least 9. So it dominates everything else. So under border count also, C4 is the winner. So let's get these to the side. So this was when we were assuming that voter 1 was voting truthfully. So they were reporting their true preferences. Let's see what happens when voter 1 manipulates and she says that C3 is my top candidate. So under this condition, you can see that, again, with instant runoff, C1 is going to go first because now no one ranks them top. But now C3 has a little edge over C2. That means that the next candidate to be eliminated is actually C2. And now it's going to be a match between C2 and C4. But in fact, C4 has n minus 1 over 2 people ranking them top, whereas you can check that C3 has n plus 1 over 2 ranking them top. So in fact, now the new instant runoff winner is going to be C3. And with border count also, by promoting C3 to come over here, voter 1 or Alice, or whatever you'd like to call her, she has given C3 2 additional votes and then subtracted 1 point from C1 and C2. So with those 2 additional points that C3 gets, that's just enough to beat C4, the previous winner. So once again, the winner is C3. And notice that Alice's or voter 1's true preferences was C3 over C4. So this is a so-called profitable manipulation, meaning that she prefers to missupport her preferences. So now let's talk about what happens when instead, as fitting into the scenario, Alice instead finds her truthful copies, her neighbors, to join the election who have the same exact preferences as she does. So if we add k truthful copies, now there's going to be k plus 1 people with these preferences rather than just 1. And now you can see that with border count. So this is where I'm going to split the 2 rules because this is where things are going to start going differently for the 2 rules. With border count, even with 2 copies alone, we actually is sufficient to give C3 an edge over C4 because with every copy that I add, C3 gets 1 additional vote compared to C4. This is exactly what happened when we moved C3 over here. And you can see that even with 2 copies, the exact same result that we would have had with the manipulation is actually produced by adding copies. So just by adding 2 copies of herself, Alice gets as good of an outcome from her preference as manipulating, as her best manipulation. Of course, I haven't proven that this is the best manipulation, but believe me that it is. With instant runoff voting, on the other hand, things look quite differently. 2 copies is not enough. In fact, if you have any number of copies that's less than n minus 5 over 4, you can see that the total number here is going to be less than n minus 1 over 4. So C1 is still going to be the candidate with the least number of votes to go to in the first round. And C2, again, is going to have an edge over C3. It's, again, going to be a match between C2 and C4. And once again, these two cancel each other out. These two add up to n minus 1 over 2. And these ones are actually roughly n over 4. So once again, C2 is going to go and C4 is going to win. So now, if with any number of copies less than n over 4, Alice actually still prefers manipulating to adding truthful copies. And even now, you can see that the exact same manipulation and the exact same profile weights different, it outweighs different number of truthful copies for different rules. And in fact, in this case, n can be arbitrarily large, so the difference can be arbitrarily large. So observing that this exchange rate between lies and votes might look differently for different rules, what we suggest in this paper is getting that question that we started with and using it as a degree of manipulability, a measure of manipulability of different voting rules. So kind of measuring the impact or the power of a manipulator over someone who is able to add their truthful copies. So I'd like to give you, and this is in the worst case. So how many truthful copies does a voter need in the worst case to produce a result as desirable as our best manipulation under that specific voting rule? And our suggestion is to use this and name this the manipulation potential of a voting rule. So I want to give you just 3 quick interpretations on the manipulation potential. One of them is what we started with the story, this get out the vote instances where voters might be clustered into communities, and then each voter can either spend time manipulating or having more people from their community who share their preferences to join the election. And under this interpretation, the manipulation potential then becomes the minimum opportunity cost of manipulation in terms of adding one more copy, truthful copy, to disincentivize manipulation. If the cost is larger than that, then voters are better off finding their community members to join the election. And of course, these get out the vote efforts happen in real life. People do drive like-minded voters to the polls all the time. A second interpretation is taking a dual approach to this. So now, instead of thinking as voters as communities, I'm thinking of each of these votes as a voter, like each voter representing a community themselves. So instead of, like, it's the same election as before, instead of thinking as this election as a election with n plus k votes, we can think of it as with just 5 voters, so just these 5 rankings. But these numbers over here kind of correspond to the number of community members. So we can think of each voter as a community and their voter weight corresponding to the number of people in that community. And under this interpretation, each community can collectively, like the community leaders can instruct their community members to vote in a very specific way, but this might come at the cost of losing members who are not interested and not willing to engage in misrepresentation of their preferences. For instance, this is our lab at CMU, headed by my advisor Vince, and so while if we're gonna vote together in some election, Vince can ask us to misrepresent our preferences in a very specific way, such as please vote that American football is better than football. And some of us might find this super egregious and we might just leave the lab. I personally would. And this might come at the cost of the voter weight of our community. So this is a funny example, but it actually does happen that at least in Australia or other countries that use these instant runoff-like rules, parties routinely hand out how-to-vote cards for their supporters. And there are actually instances where issuing tactical how-to-vote cards, so asking people to misrepresent their preferences, have come at the cost of people not showing up to vote. And then now this is the manipulation potential is the minimum cost that you must lose from your community, such that manipulating is not worth it. The dual approach, the previous one. And the last one that I think might be very interesting to this community, hopefully, is this idea of approximate strategy proofness. So as computer scientists, we don't like to give up when we get an impossibility. We try finding approximation algorithms. And even though Gibbard's Satterthwaite impossibility theorem tells us there's no non-dictatorial rule that's not manipulable, it would be really cool to have a rule that have a guarantee such as this one, saying if I vote truthfully, the utility I'm going to get is at least guaranteed to be alpha fraction of this typo of what I get by manipulating minus some beta. The problem with this kind of cardinal approach is that, at least in our classical setting, the preferences are ordinal. So we only know the ranking of the different candidates by different voters, which makes this type of like cardinal comparison really difficult, because remember that in the example before, voter one was able to change the winner from C4 to C3, which they do prefer, but this might be a tremendous win for voter one if they are roughly indifferent between their top three candidates and they really hate their last candidate. In that case, they would be really, really happy. But it might also be an insignificant change for voter one if they're roughly indifferent between C3 and C4. And there's no way to tell these two situations apart from each other just looking at the preference profile. So instead, we take a resource augment. So this type of alpha-beta analysis is unfortunately not available to us. Instead, we take an approach grounded on resource augmentation, in which the performance of an algorithm is compared to the performance of the optimal algorithm, in this case, the optimal vote, with less resources. In particular, we're comparing truth-telling with some additional voter weight to manipulating with just one voter weight. So in this case, the resources are the additional resources that we give to voters, to the voter who's considering manipulating. And this might sound very familiar to some of you. In fact, it's inspired by this classical result in auction theory, where Bloor and Klempler showed that if you have identical bidders that are like sampled IID, their valuations are sampled IID from the same distribution, then running second price sealed bid, which is simple and doesn't require any information on this distribution, with n+1 bidders is going to get you at least as good revenue as running the optimal Meyerson auction with n bidders. And of course, the Meyerson action, like manipulating, requires information and can look quite complex. And if you get it wrong, it might actually hurt you. While resource augmentation, we've inspired by these auction cases, has also been deployed in other settings like selfish routing and allocation problems to measure how many copies do you need, how much additional resource do you need to make the simple thing worth doing. And this is what we do. The simple thing is voting truthfully, and we ask how many voters do you need. Okay, now that I've given you these three interpretations, now let's actually look like what this might look for some specific rules. So I've already given you two example rules. We also have a third rule, which is quite simple. It's just plurality. Pick the candidate with the most number of top votes. And in fact, we can show that the manipulation potential of plurality is exactly n-1/2 ceiling function. And of course, to prove this, you need to prove a lower bound, which requires only one profile. An upper bound requires showing it for every profile. But let me give you what the worst case kind of looks like. For C1, for voter one to be pivotal, basically it needs to be tied between two different candidates. In this case, it's C3, the third top candidate, by just a little bit. Voter one can put C2 first instead and make the second top candidate win. And you can see that in this case, they would actually need, in order to change anything, they would need roughly n-1/2 copies, because until then, because C1 has the top candidate has so few plurality votes anyway, nothing's going to change until they get this many copies. And you can see intuitively that this is kind of a worst case, because for anything to change in plurality, at least two candidates need to be close to each other, meaning that the number of plurality votes of the winners can be at most n/2. So if you add this many copies, then you at least have your top choice winning, so you're not worried about it's definitely as good as manipulation. For instant runoff, actually things might look really bad, or like at least bad by a factor of 2, because this is actually, I'm not going over it again, it's the starting example we had, a bit more general to accommodate n number of candidates, but it's this idea that like if you vote truthfully, you're definitely gonna like kind of eliminate the wrong candidate, leading for your top fourth candidate to win. But if you change the order of two specific candidates, you can kind of go into this other branch that actually makes life so much better for you, and you would need to become the majority winner to actually get something as good. So the story is actually pretty interesting for Borda. If we had time, I would have like made you maybe guess. Yes, so in this case, we already did this, so I'm not going over it. With Borda, if we had time, I would have made you guess. But in the interest of time, I will just tell you. It's actually number of candidates -2. So these two rules, we had a linear dependence on the number of voters. But with Borda, we actually see the number of candidates, which in fact, in practice can be arbitrarily smaller, of course. And the idea is that now, if you have a profile that it's almost tied between your top two candidates, C1 and C2. But now, like C1 just has an edge. So C2, your second top candidate, has just as an edge over your C top candidate by m-2 votes, because remember, these are the number of points that we give, and this guy puts C1 last. You can actually also put C2 last and make C1 win instead, and you can see that m-2 copies is the worst case in this case, because with each additional copy, you can subtract 1 point from their difference. Yeah, so So in this case, going back to this analogy with the scales, basically different voting rules can lift different number of the same manipulation under different voting rules can lift different number of truthful copies. And if you remember, introductory example, remember that I showed you that even 2 copies was enough for a board account to get something as good as manipulation, but this is exactly equal to m-2 in this example because there are 4 candidates. Okay, so now we definitely know instant runoff is not the best out of these 3 because it's always going to be dominated by plurality. So let's look at what happens with other rule classes. In particular, positional scoring rules generalize these 2 rule classes, saying you give SJ points to your J rank candidate, and it's an infinitely large class. And we actually showed that for any positional scoring rule, the manipulation potential will be worse than at least board or plurality, meaning that for any number of candidates or voters, the best positional scoring rule, the positional scoring rule with the least manipulation potential, is either going to be board account or the plurality. So they kind of shape the entire Pareto frontier. And another glass result I'm going to share is that we actually look at Condorcet extensions, but to prove a stronger impossibility result, we significantly weaken them to this weak majority consistent axiom, which just says if there are only 2 types of rankings, so even everyone ranks ABC or BCA, then you need to go with the top choice of the majority ranking. So if 51% of the people say ABC, you need to go with A. So, of course, this is implied by majority consistency. It's also implied by Condorcet consistency. We showed that none of these rules can beat plurality. It's always going to have a manipulation potential, at least as plurality, and therefore at least as Borda, when much larger than Borda when there are more voters than candidates. And more further, this shows that no Condorcet extension can defeat plurality. And in fact, if you additionally add majoritarians to this assumption, meaning that they only decide the outcome on the pairwise defeats, then the situation looks even worse because we add another factor of 2. Okay, so that's a very quick result as the summary of our results. This is a larger summary of our results showing that, we have these impossibility results. We have also analyzed some specific rules. There are also rules that depend on both number of candidates and number of voters. That's also possible. But in this table, one thing that stands out really is that Borda count is the only rule we analyzed where the number of, the manipulation potential does not grow with the number of voters, which is, of course, really good in settings with large electors. So there's a lot of really interesting future directions. I won't get into them in the interest of time. If any of these buzzwords seem interesting to you, I would love to chat about it with you, or feel free to ask about it in the questions. So I just want to end with a quote. Of course, we as social choice theorists know that all voting rules are manipulable. This is wisdom given to us by Gibbard and Satterthwaite. But the wisdom we focused on in this paper is that some voting rules are manipulable, that some voting rules are more manipulable than others. And this is, of course, wisdom given to us by George Orwell, if he was also a social choice theorist like Alice and ourselves. And that's all I wanted to say. Thank you so much for your attention. This is our archive link. It just got out, and I'm happy to answer any questions.
Thanks, Emin. Let's give a round of applause.
Thank you.
Okay, then we can have some questions. So there were 2 questions in the chat during the talk. Errol, would you like to speak out your question?
Should I start? I'm not sure Errol's was a question. I think it was more of a remark, but I can ask my question.
Yeah, sure.
So it's very interesting. So you defined this manipulation potential with respect to the best possible manipulation. And I think you could also have a similar one just with respect to getting any kind of improvement at all. And I was wondering whether that would change things significantly. And whether why you focused on this definition rather than the other one.
That's a great question. So exactly, we could like focus on any manipulation. The reason we took a more worst case approach is because of this like idea of inspired by resource augmentation. We kind of like want to get like a worst case guarantee on kind of how much truth telling approximates like manipulating in the worst case with these additional resources. But one thing I think is really interesting and was listed out of all these additional like the future directions is this idea that like other forms of manipulativity have been studied in literature, as I'm sure some of you are familiar with. Some of these are like these frequentist approaches. So in what percent of like at 1% of profiles is there is somewhat profitable manipulation? And they're definitely right that you could combine our measure with other types of like comparing it with any manipulation. And in fact, if you had like a distribution over the voters or like just assuming impartial culture, you can also measure like the expected manipulation potential rather than the worst case manipulation potential. And
But
that is,
what I was asking is still a worst
Mhm.
case notion.
Okay. So
right, what I mean, like, what's the highest number of copies you will ever need to get some kind of improvement? That's still a worst case notion. I don't know whether it's
I see.
interesting,
Like
but,
some kind of, I think this is like while I like gave you the examples with the best manipulation, I guess this is maybe I'm missing something, but it comes down to the same thing. So you basically compare the K you would need such that the profile with your K copies is as good as getting like what you would have if you reported any votes prime.
Yeah, I'm not sure. I mean, sometimes maybe you have two manipulations possible. One gives you your second best outcome, and the other one gives you only your second to worst.
Yes.
And you are looking at the one that gives you the second to best, but maybe the second to worst needs fewer copies, but it's still a well-defined number.
Okay. Makes sense. Yeah, I guess like the first thing where something changes.
Yeah.
That
That's what
sense.
I meant. Yeah.
I think I agree with Ariel that like at least for some of the rules that we did, like Borda, like there would be the same number. In fact, for most of the rules that we did, there's one manipulation that works. So I feel like, I mean, not to don't quote me on this, but I think pretty much all the results in this paper should generalize. I don't remember a worst case profile where there were multiple different manipulations available. We kind of designed them in a way such that there's something very specific voter one can do. Also to point very quickly to Ariel's question or like point about knowledge about voting rules, not necessary. That's I think I kind of summarize our points about here, but you're definitely right, Ariel, that this has to do with the no-show paradox and the participation criterion. And in fact, like we have a section in the paper addressing that. So we kind of incorporate how the relationship between this measure and the no-show paradox to kind of have a measure that also is robust to any type of like robust to adding copies hurting you. Kind of we look at the number of copies that you would need to make sure that even if you add more copies, it would not hurt you.
So let's suppose I could prevent other voters from showing up.
Say again?
Let's suppose I could prevent other voters from showing up.
Yeah, so in that case, you would look at the minimum K such that you would get like a manipulation. So the reason that we opted for the minimum K such that for any K prime larger than K, you're good, is because we wanted to compare like this simple strategy with like something that is strategizing. Whereas like the idea of like preventing other voters from showing up do require some computation on your part. Whereas like if I give you a minimum number, then you're like, okay, if I get to this number, then you're good even if more people show up. But again, kind of similar to Ule's question, for at least for all the results in our paper, it wouldn't have made a difference. Like these types of non-monotonicities do arise where adding more copies can help you and then hurt you and then help you again. I think we have a cute example in the paper. But in the worst case, we found that like none of the profiles that we used to prove the results had any of these non-monotonicities. So even if you defined it as the minimum number of copies that you would need to get something as good as a manipulation, stopping other copies from joining, then you would get the same numbers as our table over here.
Okay, more questions?
I think Josh might have had a question on the chat about, can you repeat or elaborate on endogenous participation and which conditions enable agents to show up? if Josh
Yeah,
is
was this
here,
just your monotonicity question?
Say again?
Was this just your point about monotonicity?
Yeah,
Voting
a little
rules?
bit of that, and like this idea that like you could also think of like these voters as just like, especially with homogeneous rules, you can just think of these rules that map weights to like weights of like frequencies of each vote to the winner, meaning that like then you can think of the weight as like kind of the number of community members. And the idea, at least if you're talking about the slide where I had endogenous participation under the second interpretation, that was when I was saying that instead of looking at like how much you need to how cheap should it be to increase things such that manipulating is not worth it, you kind of can take this dual approach of like, what is your loss in weight because you manipulated, because there are settings in which like misrepresenting your vote can cost you community members, such as these like how to vote card settings. And then it's basically like this dual definition that like then the manipulation potential is the minimum cost of manipulating in terms of the weight that you're going to lose to make sure that manipulating is not going to be worth it.
And this is in the worst case? So worst case context?
Yeah, everything in this paper is in the worst case.
Gotcha. Okay, thank you.
Yeah. Of course, thanks for the question.
I'm going to read this.
Maybe I can just say something to Ule's question about why we care about the worst case. So think about maybe we have a voting rule where one manipulation worth a very small number of additional voters, but we have some other manipulation that worth a lot. This might mean that still we have incentive to strategize. So I guess the question that we try to answer is, what is the incentive a voter have to try to find the best manipulation? So if there exists a manipulation that can worth a lot in terms of additional voters, then so we try to measure the incentive. So this is why we care about worst case. Hope it make it a bit clearer.
Yeah, makes sense.
Yeah.
Worst case of the worst scenario. Yeah, I understand. Yeah,
exactly.
Thank you.
Yeah. Thanks so much, Eden. Yeah, and I guess it ties to Florian's thing as well. Like, yeah, what if you cannot stop other people from joining? It's kind of like even if you don't have control over more community members coming, even if you can do your best manipulation, then this is the number of copies that's enough to say you're not going to manipulate because it's not worth it. And I think this is very much grounded in like similar ideas in auction theory and other resource augmentation based approaches that kind of compare the worst case of an algorithm with additional resources with the optimal algorithm.
Okay, then let's start our coffee break. So you'll have the opportunity to join breakout rooms, and then we'll continue in 10 minutes. See you then. Okay, let's continue. Our second speaker for today is Hannaneh Akrami, who is at Max Planck Institute in Saarbrücken and in Bonn. Could you start sharing the slides, please?
Yes.
So you also have 20 minutes, followed by questions. The screen is yours.
Thank you very much. I hope my slides are visible.
Yeah.
Okay. Yeah, thanks a lot for the introduction and also for the invitation. It's a great pleasure to give a presentation in this seminar. This is a joint work with Ryoga Mahara, Kurt Melhorn, and Niti Rati. And it's a fair division talk where we want to divide a set of items among a set of agents in a fair manner. So let's dive into the setting. Okay. So the input is we are given a set of n agents. Let's assume these three. And we are also given a set of indivisible goods. So in this talk, I will be only talking about indivisible items. So you should assume each item as a whole must be allocated to one agent. And we also have goods, meaning that agents have a non-negative utility over the items. And also each agent is equipped with a valuation function which shows how much this agent likes each subset of the goods. And in this talk, we assume that the valuation functions are additive, which simply means that the value of each subset is just the sum of the individual goods in that subset. So this is what the input would look like, and the goal is to find a fair allocation of the goods to the agents, and an allocation is simply a partitioning of the goods into n bundles, x1 up to xn, so that xi would be allocated to agent I. Now we want this allocation to be fair, and what do we mean by fairness? There are many different notions of fairness, different categories of fairness, mainly envy-based and share-based categories. First, I will start with envy-based categories, the most important of which is envy-freeness. And as the name suggests, it means that no agent should strongly prefer another agent bundles over their bundle. So vi of xi, which is the utility agent I has for her own bundle, should be at least as much as vi of xj, the utility she has for agent j's bundle. Now we all know envy-free allocations do not always exist in the setting of indivisible goods. Simplest counterexample, two agents, one item that they both positively like. Therefore, we study relaxations of this notion. And most prominent relaxation of envy-freeness would be envy-freeness up to any good, or EFX. So under EFX, an envy from, let's say, agent I to agent J is allowed, but any such envy must be eliminated upon the removal of any good from the envied bundle. So vi of xi should be at least as much as vi of xj minus g for any good g in j's bundle. So thinking of additive valuations, this is basically saying that if I envy someone, this envy must be eliminated if I ignore the least valuable good that they have in their bundle, and least valuable according to my point of view. And yeah, the counterexample we had previously for envy-freeness is not a counterexample for EFX. Now let me give you one more definition, and that is a strong envy. We say agent I strongly envies agent J if there exists a good in J's bundle such that even after the removal of that good, the envy persists. So vi of xi is less than vi of xj minus g for some good g in xj. So in other words, an allocation is EFX if and only if there exists no strong envy between any pair of the agents. So, okay, now the question is, do EFX allocations always exist or not? And, well, this question is open. At least for additive valuations, we don't know whether EFX allocations exist for arbitrary number of agents. But this is not the end of the line. Still, so many studies has been on like attacking this enigmatic problem from different aspects. Like, for example, one could consider restricted settings where agents have more special classes of valuation functions or a small number of agents. But what I will talk about in this presentation is two important relaxations of EFX. One is called epistemic EFX and another is EF1. So let's get into their definition. We say that a bundle B is epistemic EFX feasible for agent I if there exists the partitioning of the rest of the items into n-1 bundles, A1 up to an-1, such that agent I would not strongly envy any of these bundles upon receiving B. So what it is saying is basically consider any allocation. Let's say in this allocation I got bundle B. Maybe this allocation is not EFX. Maybe I don't find this allocation EFX, meaning that I strongly envy some other agent. But I would be happy with my bundle, or I would call my bundle epistemic EFX feasible if hypothetically I can reshuffle the remaining items among the remaining agents such that in the resulting allocation, in the allocation after this reshuffling, I am not strongly envying anyone. So in that case, if such a scenario exists, I'm happy with my bundle. So this would be the definition of EFX feasibility of a bundle, and we say that an allocation is epistemic EFX feasibility of a bundle, and an allocation is epistemic EFX if all agents receive a bundle that they find epistemic EFX feasible. just to make sure we are on the same page, let's see an example. Here you see 3 agents, 7 goods. The agents have additive valuations for these goods. And let's consider the following allocation, that G1, G2, and G4 are allocated to the first agent, and so on. So I claim that this allocation is EFX, and therefore it's also epistemic EFX. Well, epistemic EFX is a relaxation of EFX. In fact, this allocation is envy-free. If you check the envy between any 2 pair of agents, you see that it doesn't exist. Hence, we get these 2 properties as well. Now let's look closely at G3 and G4. Well, G3 is very valuable to agent 1, but is allocated to agent 2, and the other way around for G4. So both agent 1 and 2 would be willing to swap these 2 goods among themselves. So let's say we do this swap. Now all of a sudden the allocation stops becoming EFX, and it's not because of agent 1 and 2. They are still not even envying anyone. It's because of agent 3. So although nothing had changed for agent 3, she's getting the bundle that she had previously. But because she's strongly envying agent 1 now, she doesn't find the allocation EFX anymore. So now she feels that this allocation is not fair because, well, nothing had changed for me, but all of a sudden agent 1 is getting too much, and I'm not happy about that. So the allocation stops becoming EFX, but it is still epistemic EFX because, well, agent 1 and 2 are anyways fine. For agent 3, we know that there exists another partitioning of the other goods, namely the allocation that we saw in the previous slide, in which agent 3 is not strongly envying anyone, having the same bundle that she has right now. Therefore, her bundle is epistemic EFX feasible, and the allocation is epistemic EFX. Okay, I hope the definition is clear. Now, let's see what is known about this notion. Well, it was shown that it exists for additive valuations in 2023, and then in 2025, it was shown that it exists for monotone valuations. So why did I even bother you with all these definitions if this is basically, if we know everything or almost everything about this, fairness notion? Well, let me bore you with one more definition and then I will get to the point. And that definition is envy freeness up to 1 good, or EF1. So an allocation is EF1 if, again, the envy, like an envy from agent I to agent J is allowed, but this time there must exist a good in agent J's bundle that if we remove that good, then the envy is also removed. So it is weaker than EFX. EFX for additive valuations was saying that upon ignoring the least valuable good, I should stop envying another agent. And EF1 is saying that, oh, if the envy is gone, even when I ignore the most valuable good of the other agent, I'm still happy. Okay, so it is also a relaxation of EFX, and same story as epistemic EFX. For EF1, we know that it exists for, well, a simple folklore round-robin algorithm proves that it exists for additive valuations, and even for monotone valuations, we know that it exists. Okay, so now finally I can come to the question that we answer in this work, and that is whether we can satisfy, whether we can guarantee EF1 and epistemic EFX at the same time. So whether there exists allocations that are EF1 and epistemic EFX simultaneously. So before giving you the answer to this question, let me first discuss why this question is interesting or important at all. Well, EF1 and epistemic EFX individually, well, they are clearly less fair than having both of them at the same time. And having both of them at the same time is less fair than having EFX, because both of them are weaker than EFX, and therefore EFX implies both of them. So, and we know, or at least it seems, that answering the EFX existence problem seems to be very difficult. So it could be easy. It could be a simpler question to answer, whether EF1 and epistemic EFX can be satisfied at the same time, rather than jumping into answering the EFX question. And I mean, everything else, like the first 3 bullet points are basically all implied by the first line that we have here. I just want to emphasize what implications we get for the EFX problem. So note that if the answer is no for this question, if there exist instances in which no allocation is EF1 and epistemic EFX at the same time, then immediately we get a no answer for EFX. Because if there was an EFX allocation, we would get these two. And also, even if at some point we answer the EFX question, or someone answers the EFX question negatively, so we know that EFX cannot be guaranteed always, this is still a valid question to ask, whether we can, guarantee EF1 and epistemic EFX, which is weaker than EFX, so maybe we could not satisfy that, but we can possibly satisfy this. Okay. Now, what is known about this this question? Well, basically nothing. Nothing more than we know about EFX is known for this relaxation of EFX. So clearly, we know that it exists in all the settings in which EFX exists. So in particular, for additive valuations and for agents, EFX is not known, and therefore we also, at least prior to this work, we didn't know whether EF1 and epistemic EFX at the same time could be guaranteed, even for 4 agents with additive valuations. And our result is that, well, EF1 and epistemic EFX can be guaranteed simultaneously when agents have additive valuations. Okay, so I will give I will not get into the details of the proof. I will more give a roadmap of the proof and actually talk about the building block of how we get this result. So the building block, or the technique that we use, which is not which has been used previously several times in the literature, called the lone divider technique, is as follows. So consider any desirable property P of a bundle for an agent. So this property could be like the EFX feasibility of this bundle B for agent I, or it could be whether this bundle has a certain utility, at least a certain utility Ti for agent I, and so on. But it must be the property of the bundle itself, and it should not depend on how the rest of the items are distributed. Now, for any partition of M into N bundles, A1 up to AN, consider the following bipartite graph. On one part, we have the bundles, A1 up to AN, and on the other part, we have the agents, 1 to N. So these are the nodes of the graph, and then there exists an edge between agent I and bundle AJ if agent I finds this bundle AJ desirable according to the property P that we set initially. Okay, so this is the graph, and we call a matching good if no unmatched agent has an edge to a matched bundle. So consider the matching that we have here that matches A1, A2 to agents 1 and 2. This matching is good because none of the agents 3 to N have an edge to the matched bundles being A1 and A2. So the idea of this technique is to cleverly initial partition and consider this graph and iteratively find a good matching and then match the bundles to the agents according to this matching, remove them from consideration, and then solve the problem for the smaller instance. In particular, the way that we find the initial matching, the initial in each round is the following. So in each round, we pick an arbitrary agent I who has remained, and we ask that agent to give us a partition, A1 up to AN, such that she has an edge to all of these bundles. She finds all these bundles desirable. Well, clearly, whether this is possible or not depends on this property P that we are setting initially. But let's say that is possible. So this agent I is playing the role of the lone divider in this round, and hence the name lone divider for this algorithm. Okay, so the agent A does this, and then we consider the graph, while other agents might also have some edges to the bundles. And then we find a good matching. And what we do is just that we remove this matching. We allocate the bundles according to this matching and then remove them. And then if there exist some agents that are remaining, which there are in this case, we continue. We again pick an arbitrary remaining agent. That agent would play the role of the lone divider, and so on. So this is already a framework that exists. Now, if we want to use it for some property, let's say for proving EFX and EF1 and anything, all we need to show is to prove that the second bullet point here goes through, that in each round you can in fact find an agent who could play the role of the lone divider for you, who could give you this partition. This is the only thing that we need to prove, and it depends on the property P. The existence of the good matching follows from, it does not depend on the property P that we are having. It's a property of the graph that we are studying, and it always exists if the lone divider exists, if an agent could be a lone divider. Okay, so this was kind of the high-level idea, or actually the whole algorithm of lone divider. Now remember, we wanted to prove EF1 together with epistemic EFX. But what we know for sure is that this lone divider does not guarantee EF1, because it has this kind of myopic behavior that the agents that are removed in earlier rounds are completely removed from consideration, and they don't have anything to say about the bundles that are formed later. Maybe they strongly envy them, maybe they value those bundles a lot, such that even EF1 would not be guaranteed. But there exists an extension of this algorithm, which I will not explain. We will just use it as a black box, which does the following. So basically, we know that if we can guarantee certain thresholds T1 up to Tn, these are the values that we can guarantee for agents 1 to n, using this lone divider technique. We know that there exists an extension of this algorithm, let's say extended lone divider, that guarantees not only these shares, these T1 up to Tn thresholds, but also it guarantees EF1 on top of that. So it gives us an allocation that guaranteed the utility that we could guarantee for each agent in the lone divider technique, plus that the final allocation is also EF1. Okay, this is more similar to what we are looking for. Now, if I tell you that that lone divider guarantees epistemic EFX, even for monotone valuation. So using the lone divider technique, we can get epistemic EFX. Can we use this black box as it is and obtain like the existence of epistemic EFX and EF1 at the same time for monotone valuations? Okay, in the interest of time, I will answer this question right away. And the answer is no, because epistemic EFX is not a share-based notion. Now, I didn't really define the share-based notions of fairness, but what I mean is that epistemic EFX is not a property of the utility of the bundle. So maybe there exists a bundle that I find epistemic EFX feasible, and then you offer me another bundle that I value more. My utility for that bundle is higher, but the second bundle is not epistemic EFX feasible for me. So here is the catch, that we cannot use the lone divider technique, or we cannot use the extended lone divider technique just blindly, because all that it gives us is the utility that we could guarantee initially with the lone divider technique, and the extension then also giving us EF1. Okay, but We still use this technique, and the way that we use it is we define a share-based notion that would imply epistemic EFX, and then prove that lone divider works for that share-based notion. So the share-based notion that we define is called strong EEFX share, which, in order to see what it means, let's have a visualization. So let's say that for agent I, we sort all the subsets of M in non-decreasing order of value. So S null would be the empty set, S2M minus 1 would be the set of all the items. And then we, like the bundles that are EEFX feasible for agent I are the green bundles, and the EEFX infeasible bundles are the red ones. So this strong EEFX share that we are defining is a share that implies EEFX. So basically it would be the value of the leftmost green bundle such that everything to the right of that is green. So it is the value of a bundle such that we know any subset having larger or equal value than that is epistemic EFX feasible. And it is well defined because the set of all the items itself is epistemic EFX feasible. So we have a green bundle on the right. So I hope the definition is clear. But even if it's not, the point is, like, the way that it helps us is that it is a share-based notion that implies epistemic EFX. And that's all we care about. Because the way that we prove, like the way that is helping us is that we prove that this lone divider technique guarantees this share-based notion, this strong EEFX share for additive valuations. That is what we could prove, which immediately, using that black box, that extended lone divider, gives us that this extended lone divider guarantees EEFX and EF1 for additive valuations, which is what we were looking for initially. So let me repeat myself. Our main result is that EF1 and EEFX can be guaranteed simultaneously for additive valuations. And the way we do it is that we define a share-based notion. That, and the property of this share-based notion is that it implies EEFX. And then we prove that the lone divider technique proves or guarantees this share-based notion. It guarantees a strong EEFX share for all the agents if they have additive valuations, which, using the black box, gives us this share-based notion, this strong EEFX share plus EF1 for free, just using a black box that already exists. And because this share implies EEFX, we get what we wanted initially. So we get EEFX and EF1 at the same time. Okay, I hope that the roadmap was clear. Now let me finish my talk by suggesting some future directions. And that is, well, our result holds for additive valuation, but we know that EEFX and EF1 individually exist for monotone valuations as well. And it is a valid question to ask whether they can be guaranteed at the same time for this class of valuations. And also our results hold for the good setting. One can ask the same question about chores. Again, individually EEFX and EF1 exist for chores setting, even for monotone valuations. And finally, our proof is an existential proof, which can be turned into an constructive exponential time algorithm. But we don't know whether there exists a polynomial time algorithm for additive valuations that could guarantee these two notions at the same time. For additive valuations, guaranteeing each of them individually is possible in polynomial time. Okay, that's it from my side. Thanks a lot for your attention.
Thanks, Hannah. Let's give a round of applause. Could you please unshare your slides so that we can all see each other?
Yes.
Okay, great. Good. So, who has questions?
Okay, on the complexity of finding an EF1 and EEFX, is it possible to verify in polynomial time that an allocation is EF1 and EEFX? So this is definitely, we can verify whether it is EF1. I don't think we can verify whether it is EEFX. I'm not. Yeah, exactly. Verifying EEFX alone is NP hard.
Yeah, you can. I was just hoping if there was any chance that, maybe if we only look at EF1 valuations, then maybe verifying EFX might be easier, but that was the question. Oh.
Sorry, was it an extra question or was it the same question?
It was the same question. Yes.
Okay.
So one way to look at epistemic EFX is that a single agent cannot detect that the allocation isn't EFX. And like one could generalize this by saying that multiple agents, like let's say 2 agents, can never detect by just looking at their own allocations that the entire allocation is not EFX. Sort of a stronger requirement.
I see.
And I asked earlier whether it's anything about the existence of such allocations is known, and the answer seems to be no. But have you thought about it at all?
So you mean like if I have extra information about, I have information about my bundle, but maybe I also have information about one other agent's bundle.
Right. Mm-hmm.
It's definitely very interesting. I haven't seen anything on on this.
For example, it's like at least as hard as proving existence for 3 agents. Right. So because if you have only 3 agents and 2 agents allocated, then the remaining one. Yeah.
For 3 agents, if I know, if agent 1 and 2 know their own bundles and agent 3 only knows one of their bundles, I think it is still simpler than EFX.
I think one way to formulate it would be to say that no pair of agents can detect that the allocation is a...
I see. Mm-hmm. So there is a question whether the complexity of verifying EFX is open. I actually don't know if it's published or it's just something that I heard that some group proved that it's NPR, but I don't know actually if it's if there is a reference for that.
And what about combination with PO, as Dominic asked?
Right. So no, epistemic EFX is not compatible with PO. Basically the counter examples for EFX and PO also works for epistemic EFX and PO, like for 2 agents.
Shouldn't EFX be closed under Pareto improvement?
EFX, we know that EFX and PO cannot be guaranteed simultaneously if we have if we allow utility 0 for some of the goods. As far as I remember, the same or very similar examples also showed that epistemic EFX and PO cannot be guaranteed at the same time. I see. Yeah, that's true. Like Yanis's comment, it depends on how you define EFX. Like whether you allow marginal 0 utilities or not. Whether the NV should be removed upon removal of any good or upon the removal of goods that actually bring the utility down.
Yeah, I think for one case we know that that they are not compatible. For the other case, we just don't know.
Exactly. For the other case, it's open.
If you allow for sufficiently general utility functions, do you know that EEFX allocate EEFX plus EF1 allocations fail to exist?
No, we don't know. In fact, the framework that I described could work also for monotone variations. If someone proves that this is strong EEFX share could be guaranteed by the Sloan divider technique, then we immediately get that it also, both of them together exist for monotone valuations. It's just that our proof only works for additive valuations.
Okay, so good. So last chance to ask more questions.